Verifying the integrality gap, we now construct the integrality gap verifier for CAP. Recall that it receives as input weights WIS and outputs an integral allocation x to the L, which is a C approximation to the social welfare with respect to WIS. Two requirements differentiate it from a regular C approximation for CAs. One, it cannot assume any structure on the weights WIS. Unlike CA, where we have non-negativity and monotonicity, and two, the obtained welfare must be compared to the fractional optima. Usually we care for the integral optimum. The first property is not a problem. Claim 12.19, given a C approximation for general CAs A prime, where the approximation is with respect to the fractional optima, one can obtain an algorithm A that verifies a C integrality gap for the linear program CAP with a polynomial time overhead on top of A. The requirement to approximate the fractional optimum does affect generality. However, one can use the many algorithms that use the primordial method, or a de-randomization of an LP randomized rounding. Simple combinatorial algorithms may also satisfy this property. In fact, the greedy algorithm from Chapter 11 for single-minded players satisfies the requirement, and a natural variant verifies a square root of 2 times square root of n integrality gap for CAP. Definition 12.20. Greedy revisited. For the set WIS such that IS is in E as the input fixed at, construct X as follows. Let IS equals to the argument maxima of Wi prime S prime over the square root of the size of S prime, where the maxima is taken among the pair I prime S prime in E. Set xis equals to 1. Remove from E all I prime S prime with I prime equals to I, or S prime intersect S is not empty. If E is empty, reiterate. Lemma 12.21. Greedy is a square root of 2m approximation to the fractional optimum. Greedy is not truthful, but with the decomposition-based mechanism, we use randomness in order to plug in truthfulness. We get the following theorem. Theorem 12.22. The decomposition-based mechanism with greedy as the integrality gap verifier is individually rational and truthful in expectation, and obtains an approximation of a square root of 2m to the social welfare. Remarks: the decomposition-based technique is quite general and can be used in other cases if an integrality gap verifier exists for the LP formulation of the problem. Perhaps the most notable case is multi-unit CAs, where there exist B copies of each item, and any player desires at most one copy from each item. In this case, one can verify a big O of m to the 1 over b plus 1. Integrality gap, and this is the best possible in polynomial time. To date, the decomposition-based mechanism is the only truthful mechanism with this tight guarantee. Nevertheless, this method is not completely general, as VCG is. One drawback is for special cases of CAs where low approximation ratios exist, but the integrality gap of the LP remains the same. For example, with submodular valuations, the integrality gap of CAP is the same. The constraints do not change, but lower than 2 approximations exist. To date, no truthful mechanism with constant approximation guarantees is known for this case. One could in principle construct a different LP formulation for this case with a smaller integrality gap, but these attempts were unsuccessful so far. While truthfulness in expectation is a natural modification of deterministic truthfulness, and although this notion indeed continues to be a worst-case notion, still it is inferior to truthfulness. Players are assumed to only care about their expected utility and not about the variance, for example. A stronger notion is that of universal truthfulness, where players maximize their utility for every coin toss. But even this is still weaker. While in classic algorithmic settings, one can use the law of large numbers to approach the expected performance. If the mechanism decides one cannot repeat the execution and choose the best outcome as this affects the strategic properties, deterministic mechanisms are still a better choice.